Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to do an example with conservative vector fields. So here we're given this vector field f, we want to show that it's conservative, and then we want to find a potential function for the field. So a vector field is conservative. There are a few different ways to characterize it, but it's conservative if and only if the work done around a closed path is 0. So we can use integrals to calculate the work done. Or another way we can think of this is a vector field is going to be conservative if we can express f as the gradient of some function phi. And actually this function phi is the potential function here. So what we want to do is show that our vector field is conservative and then find this function phi that the field is the gradient of. So there's yet another way to characterize conservative vector fields, and that's going to be true if the partial derivative of p with respect to y is equal to partial derivative of q with respect to x, where p is the first component, really p of x comma y, and q is the second component. So to show that f is conservative, we really only need to verify that this equality holds for all x and y. So let's go ahead and do that. Now in our case, p sub y, the partial derivative of p with respect to y is just going to be 2y. Okay? So we have y squared plus 5, take a derivative with respect to y, we get 2y. What about q sub x? So here, only slightly more complicated because now we actually have x's and y's in q. So the partial derivative of q with respect to x is going to be 2y, right? Because minus 8, that just becomes 0 in the derivative because it's just a constant anyway. But for the 2xy term, remember we can rewrite that as 2y times x, and we're taking the partial derivative with respect to x, so we treat all of our y's as a constant. So this is essentially just a constant multiple of x. And when we take the derivative of x with respect to x, we're just going to get, or when we take the derivative of this whole thing with respect to x, we just get the constant multiple part back. Okay, so that's just going to give us 2y. And we see that these are in fact equal to each other. So since p sub y equals q sub x, then we see that f is in fact conservative. Okay, so now we're going to go ahead and look for this function phi. So we know now that we can express f. Well, let's go ahead and rewrite f. So f is y squared plus 5 and 2xy minus 8. Let's make that a little neater. Minus 8. And we want to express this as the gradient of some function phi. So remember, the gradient of a function phi is really del phi del x, comma, del phi del y. So what that means then is that del phi del x equals y squared plus 5, and del phi del y equals 2xy minus 8. So let's go ahead and write those down. Del phi, let's use the same colors. Del phi del x equals y squared plus 5, and del phi del y equals 2xy minus 8. So we have these two equations that we want to solve, and when we solve these equations, we're going to get our potential function phi. All right, and then we'll be done. So let's go ahead and go to page 3. So the equations that we want to solve are del phi, let's use different colors here. Del phi del x equals y squared plus 5, plus 5, plus 5. And over here, we're going to have del phi del y equals 2xy minus 8. So we just solve these one at a time individually, and then we combine the results, and we'll talk about what that means when we get there. So here we're just going to basically want to integrate both sides with respect to x. Let's separate these. Integrate both sides of this with respect to x. So on the left, we're just going to get phi, right? So if we integrate this with respect to x, we're just going to get the phi back. And what happens over here? Well, as far as x is concerned, this is pretty much, these are both just constants. So when we integrate with respect to x, we're just going to get y squared times x plus 5 times x plus an arbitrary constant. However, in this case, our arbitrary constant is actually going to be an arbitrary function of y. And why is that? Because when we differentiate or integrate this function with respect to x, then remember we have to treat y as a constant. So our arbitrary constant of integration, because this really is indefinite, it's an indefinite integral, our arbitrary constant really needs to be an arbitrary function of y, because as far as this operation is concerned, y is a constant. So let's go ahead and say that we have some arbitrary function, little f of y. And then let's go ahead and simplify that a little bit. So phi of x comma y equals xy squared, that's a squared, plus 5x. So let's fix all of this. So we have equals xy squared plus 5x plus f of y. Okay, that is our phi of xy over here. Now what happens over here on the other side? Now we're going to integrate both sides with respect to y. We're going to get phi equals, so when we integrate on the left, we just get the function phi back. What happens when we integrate on the right? Well, 2xy, if we integrate that with respect to y, then we're going to get xy squared, right? And then we have minus, because the 2x is just really a constant multiple, so the 2 is going to come back up here because we already have a y. So really what that is 2x times 1/2 y squared, and then the 2 and the 1/2 cancel, leaving us with just xy squared. So that's really what's happening there. And then minus 8y, and then plus, again, we have an arbitrary constant, but our arbitrary constant is really supposed to be an arbitrary function of the other variable, which this time is x. So let's say little g of x. So our arbitrary function of integration is little g of x. So here we have a phi over here. So phi of x comma y, phi of x comma y is xy squared minus 8y plus g of x. All right, now we combine our two results together. So let's go ahead and give ourselves some room. And we have two expressions for the same thing. So that's phi of x comma y. We have this expression for phi and this expression for phi. So those expressions both have to be equal to each other. In other words, xy squared plus 5x plus f of y equals xy squared minus 8y plus g of x. Okay, so notice we have an xy squared in common on both sides, so we can subtract that from both sides. And then that's going to leave us with 5x plus f of y equals, let's say, g of x minus 8y. So notice now, what we want to do is find f of y and g of x, and we can directly from these equations, from this equation here. So g of x is supposed to be some arbitrary function of x, and that's what we have over here. We just determined it. It has to be 5x, and so that's g of x. And likewise, f of y has to be minus 8y. Right? Now, how can we deduce that automatically from this? Well, because we know this equality has to be true, because what we have are two different expressions for phi of x comma y. So these two different expressions, by the transitive property, have to equal each other. And if they equal each other, then this equality here has to be true. And the only way for this entire equality to be true is if g of x is 5x and if f of y is minus 8y. So now we can actually get our, we can finish the problem and get our function phi. So let's separate more space up here. And we can say, finally, that phi of x comma y has to equal, now we can use either this one or this one. It does not matter at all which one. If we use this one, then we already have our g of x, it's plus 5x. If we use this one, we already have our f of y, it's minus 8y. Okay, so it really doesn't matter which one we use. But in any case, we're going to get, if let's, formally I guess we'll use this one. So we're going to have xy squared plus 5x plus f of y, but f of y is minus 8y, so then we have minus 8y. Okay, so xy squared plus 5x minus 8y, that's our potential function. So phi of x comma y is xy squared plus 5x, let's make that 5 a little neater, plus 5x minus 8y. All right, that is our potential function phi. And remember, this function phi is the potential function, meaning it satisfies that the gradient of phi is equal to the vector field here. All right, so this has been an example with conservative vector fields. I hope you found this video helpful, and thank you for watching.